Hello everyone, welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over the spontaneity of processes and reactions and the entropy of surroundings. So we all know that water freezes into a solid below 0 degrees Celsius, and we're all familiar with how water vapor condenses into a fog at early in the morning, crisp, cold morning. So we see the fog. And so we realize, or we should know at this point from my previous videos, that these are going to be decrease in entropy. So this results in a decrease of entropy in the water, right? So water is going to go from a liquid to a solid. It's going to be less random, right? Energy is going to be more condensed, or I should say less condensed, but the particles themselves are going to be more structured. So there's less randomization in the water because the water molecules are going from a moving around with each other, so more freedom of motion to more of a tight structure where the molecules are locked into place, and there's a regular structure to the water. Same thing with same thing with fog, right? You're going from water vapor and you're bringing the molecules together and to form a liquid. So there's less randomization there in the water, right? So both of these involve a decrease of entropy. So then the question is, well, why are these processes spontaneous if it's a decrease in entropy? And the thing to keep in mind when you're thinking about the decrease in entropy or the increase of entropy in the system or a process is to think about the law of the second law of thermodynamics. So the second law of thermodynamics says that for any spontaneous process, it's the entropy of the universe has to increase. That is a criterion of a spontaneous process. So it's not the entropy of the system that we're looking at, it's the entropy of the universe. So in these processes, we're looking at the system. It's definitely true that the entropy of the system is decreasing, but as long as the entropy of the universe is increasing, it could be a spontaneous process. So the equation we want to keep in mind is that the change in the entropy of the universe is equal to the change in the entropy of the system plus the change in entropy of the surroundings. So we want an entropy of the universe that is greater than zero. We want a positive change in the entropy of the universe, or we want an increase in the entropy of the universe. So here, as long as if we have we can have a decrease in the entropy of the system. So the change in the entropy of the system could be negative here, and that's fine as long as the change in the entropy of the surroundings increases by a larger amount. So entropy of the system can decrease. That's fine. Delta S of the system, the change in entropy of the system can be less than zero, so less entropy, as long as the entropy of the the entropy of the surroundings is going to be increased by a greater amount. So the entropy of the surrounding, the positive change in the entropy of the surrounding is going to be greater, should be greater than the negative change of the entropy in the system, right? So here we have kind of a diagram to kind of show that this equation here. So here we have a decrease or a negative change in the entropy of the system. And here we have a greater positive entropy change in the surroundings. So when you add these together, we get an overall positive or increase in the entropy of the universe, right? And so the thing to keep in mind is like, well, okay, so how is this possible, right? So what's happening to the freezing of water or the condensing of the water in the fog? Well, when that happens, where is the energy flowing? Where is heat flowing in the process, right? So how do you get water to freeze? You got to take energy out of it. Heat's got to come out of it, right? So the heat is transferring or flowing to the surroundings. So you're going from the water, say ice. So for melting ice below, we're freezing ice below 0 degrees Celsius. Then while we're freezing the ice, we're taking energy out. So energy is flowing from the water to the surroundings so that the water can freeze. So during the freezing process, heat is flowing out from the water into the surroundings. Same thing with water vapor condensing, right? So you got water, and in order to do that, you have to take energy out. What happens when you take energy out? So you're removing the energy from the molecules. That means they're going to be moving slower, right? So remember the heat in the substance is related to how fast the water molecules are moving, or the molecules themselves are moving. So if you take energy out of the molecules, they're going to move slower. Then you got the intermolecular forces taking over. They're going to attract each other and pull them closer, and they're going to stick together, right? So that's the process. So in order to get that to happen, you have to remove energy from the system. Heat's got to go out of the system into the surroundings. So when that happens, the energy is going in the surroundings. You got a lot more space in the surroundings, a lot more molecules that can pick up that energy, and then they can spread out. So you want to think about entropy as a dispersal or randomization of energy, right? So here you're taking the energy out from, say, this water, right? So you got like an ice cube tray or something, and they'll put in the freezer. Well, what's happening? So the heat from the water in the ice cube tray or ice cube hole, or the place in the tray, that's going to go out of the water, and then that's going to go into the surrounding air, right? So the air molecules, you got a lot more of those. So then that energy can disperse and randomize the molecules that in the surrounding air, and you got a lot more space, a lot more molecules that can absorb that energy and then disperse outwards. So the surroundings is going to become the entropy is going to increase more in the surroundings because you got that larger dispersal or randomization of energy in the surroundings compared to the decrease in randomization of the molecules in the water. So keep in mind that entropy is a dispersal or randomization of energy. And so this explains why exothermic processes will increase the surroundings. And so this is why most spontaneous or many spontaneous processes are exothermic, because the exothermic process increases the entropy of the surroundings. Endothermic processes decrease the entropy of the surroundings, right? Because what's happening in an endothermic process? Endothermic means that they are absorbing heat from the surroundings. So energy is going from the surroundings to the system. And so that's going to be a decrease in entropy of the surroundings because they're losing energy, and the energy is becoming more concentrated into the system during the process. So I hope this is helpful. If this helps explain things or clarify things for you, that's excellent. Please do me a favor and like my video. Hit that like button right there. And subscribe to my channel. Hit that notification bell up there so you can be notified by other videos I put out. And also put a comment down in the comment section. Let me know what you think. I'd like to hear from you. Ask me questions if you got them. Thanks for joining me, and have a great day.